Welcome to the video on implicit differentiation. Implicit differentiation. So let's say that I have, let's just explain the difference between implicit and explicit first. So if I had a function that was, let's say, y is equal to, I don't know, x squared plus 2x plus 3. In this situation, y, the variable y, is defined explicitly in terms of x. How do I know that? Well, if you give me an x, I can just input it into this expression right there, and I explicitly get y. Right? It just pops out of the equation. But on the other hand, what if I had something like this? What if I had x squared plus y squared is equal to 100? Well, now, if I give you an x, you still can figure out a y, but it's just not as easy, right? You would, if I said x is equal to, I don't know, x is equal to 9, you would put 9 in here, you would get 81 plus y squared is equal to 100. You would subtract that from, you get y squared is equal to what, 19? I don't know if these numbers are weird. And then you get y is equal to the plus or minus square root of 19. Right? So you still could solve for y, but you had to, but this expression right here, or this equation, defined y implicitly. And, that's the different, when people use the word explicit or implicit in everyday language, it's the same thing. When you say, he explicitly said this, that means, I am hungry. I explicitly stated that I am hungry. But you could implicitly state that you're hungry. You could say, oh, well, I haven't eaten for a long time, and, boy, it would be nice to maybe eat something. And that would be kind of an implicit expression of your hunger, because someone would have to kind of do a little bit of work to come to the conclusion that you're hungry instead of you telling them. So with that out of the way, let's actually do some differentiation. So everything you've learned about differentiation right now has been explicit differentiation. So example, for this function, we know how to take the explicit derivative here. Well, it's an explicitly defined function, so we just take the derivative. We apply the derivative operator. We take the rate of change of both sides of this equation with respect to x. So you could view it like this. We're taking the derivative operator. I know this is getting messy. We're taking the derivative operator on that side, and we're also taking the derivative operator on this side. I know that. I didn't plan to write that there. That's why it looks a little. So what happens? Well, on the left side, the rate of change at y changes with respect to x. Well, we just write that. The rate of change of y, for every small change in y, what is a change in x? That equals, and then we know how to do this type of derivative. This is just a simple quadratic, so that equals 2x plus 2 plus 0, right? So there we do. We just did some explicit differentiation. So how do we do the same thing here? Well, we're going to do the same thing. We're going to apply the derivative operator to both sides of this equation. So let me do that. I'll do that in a different color. Let me erase all of this too, because this is kind of obvious things that you might already know. Let me erase all of that. Okay, so I'll take the derivative operator to both sides of this equation. So this is no different than what we did up here. And as you learn in algebra, anything you do to one side of the equation, you have to do to the other side of the equation. Otherwise, it would no longer be an equation. Take the derivative operator, because we're taking the derivative with respect to x. We could have taken it with respect to y. Of x squared plus y squared is equal to, we have to take the derivative of both sides, right? Is derivative of 100 with respect to x, right? So this equals the derivative with respect to x. Let me put it in brackets. I was going to do parentheses, but I think of x squared plus the derivative with respect to x of y squared. And what's the derivative with respect to x of 100? For every change in x, how much does this change? Well, it doesn't change at all. It's going to stay 100, right? So this is 0. The derivative of a constant, really with respect to any changing variable, is going to be 0. So that was just 0. And what's the derivative of x squared with respect to x? Well, we did that up here, right? When we took this derivative, we just took the derivative of each of these terms. The derivative of x squared with respect to x, well, that's just 2x. So we get 2x plus. Now this term here is where you might get a little bit confused. I am taking the derivative of y squared with respect to x. The derivative of y squared with respect to x. So let me take you on a side, and you shouldn't do this every time that you do one of these implicit differentiation problems, but I'm doing this because I want you to understand what we're doing. So let's say I just defined g is equal to y squared, right? So let's say that this was g, and I want to take the derivative of g with respect to x. So I apply the derivative operator on both sides of this. So let me do that. So the derivative, let me do that, d of x on that side, d of x on that side. That's a d. There you go. So what we get is the derivative of g with respect to x is equal to the derivative with respect to x of y squared. Right? And so far we haven't really done much. I've just rewrote things. But what does the chain rule tell us? What does the chain rule tell us? The chain rule tells us that the derivative, let me stay in the same color. I was switching colors. The derivative of any variable with respect to x, or with respect to another variable, is equal to the derivative of g with respect to y times the derivative of y with respect to x. And you could view this, if you don't have the full intuition of the chain rule yet, there's a couple of ways to view it. All of these dg's and dy's that you see throughout integral and differential calculus, all these really mean are a really, 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 really small change in g, a really, really, really small change in y, a really, really small change in x. So you can almost view these. So if you have when you multiply this out, this really, really small change in y is the same as this really, really small change in y. So if these are essentially fractions, so you could cancel these out, and that's why you would get the derivative of the change in g with respect to x, or the derivative of g with respect to x. So this is what the chain rule tells us. So given that this is what the chain rule tells us, how does that help us figuring out this? Well, we know that the derivative of g with respect to x is equal to the derivative of g with respect to y. Well, we already know that g is equal to y squared. I just made that definition. That's where we started from. So what's the derivative of g with respect to y? Well, that's just 2y. Right? Just using our derivative rules, or our polynomial rules, which hopefully you believe actually work, because there are several videos where we prove it. And then times the derivative of y with respect to x, which we don't know. And that's actually kind of what we're going to try to solve for. So the derivative of g with respect to x is 2y times the derivative of y with respect to x. Well, g is just the same thing as y squared, right? So the derivative of this is g. And you don't, normally when you do this, you don't have to go through the whole problem of substituting for g. I just wanted to give you that intuition. So what's this derivative right here? Well, it's going to be the derivative of this expression with respect to y from the chain rule. So that's 2y times the derivative of y with respect to x. Derivative of y with respect to x is equal to 0. When you do it mechanically, it's actually quite simple. You just say, oh, well, let me pretend like y is like an x, take a derivative, and I multiply it times the derivative of y with respect to x. Mechanically, it's very simple, but I really want you to understand that intuition, that this is coming out of the chain rule. And actually, the chain rule itself is not this, bizarre concept. It's really you're just multiplying fractions. So let me clear up some space here, and we can finish this problem. And then I'll do a problem where you have to do implicit differentiation. And even in this one that I just gave, it's really useful to do implicit differentiation. So I could clear this guy out up here. Clear that out. I could clear all of this stuff out. There we go. Clear all of that out. Ready to do some more work. So now we could solve this for the derivative of y with respect to x. So we get, let's subtract 2x from both sides. So we get 2y dy dx is equal to, I'm just subtracting 2x from both sides, minus 2x. And then what do we get? We get dy over dx is equal to, divide both sides by 2y. The 2's cancel out. You get minus x over y. And this is interesting just as it is, right? Because what was this? This was the equation for a circle with radius 10, right? R squared. And if you know your trigonometry and all of that, this tells you that the slope of a circle at any point is equal to the negative of the x over the y. Well, we know from trigonometry that the x is the cosine and the y is the sine, and so that tells you something interesting about how the derivative is related to the tangent and all of that. But anyway, I won't go into that. We're just learning implicit differentiation here, but it's sometimes fun to just think about things. So how is this different from everything else we've learned so far? Well, here we have the derivative. The derivative is actually a function of both the x and the y value. And if we feel really uncomfortable having this y here, if we don't like that, what we could do is we can substitute. So let's solve for y here. We get y squared is equal to 100 minus x squared. And then you get y is equal to the plus or minus square root of 100 minus x squared. And so you just substitute that in here. So you get another way of writing the derivative of y with respect to x. Sometimes you'll see y prime. I'm just switching notation just so you're familiar with it, is equal to minus x over the plus or minus square root of 100 minus x squared. And to some degree, since we have plus or minus down here, this minus sign, it kind of doesn't matter, right? Because when it's a minus here, it becomes a plus. When it's a plus, it's a minus. So you can kind of ignore this. That's something interesting for you to think about as well. But anyway, and this was interesting because our traditional way of solving derivatives, we had never seen a plus or minus here. So that might be a little bit interesting to you. So now let's do a problem that is actually a bit of a trick problem. It's not a trick problem, but it's actually something that I think I first saw it either when I was practicing for the AP Calculus exam, or I actually saw it on the AP Calculus exam. So it's something that you might encounter, but it's really neat. Let's say I have y is equal to x to the x. So at first you say, oh, this looks easy. Maybe I could use the power rule, but no, chain rule, but I have two x's here. And I mean, you might want to just pause and think about this for a little bit, because this actually isn't that straightforward a problem. And even though right here y is explicitly defined in terms of x, right? If I give you x, if I say x is 3, well then y is 3 to the third, y is 27. So this is an explicit function. I've explicitly defined y in terms of x. But it's very hard to differentiate explicitly. And here is the trick. Let's take the natural log, or actually you could take any logarithm, but let's take the natural log of both sides of this equation. So you get the natural log of y is equal to the natural log of x to the x. And why did I do that? Because now I can use what we know about logarithm properties. We know that log of a to the b is equal to b log of a. Right? And you could watch the exponent properties videos if you forgot that. So let's rewrite this like using this property. And I'm going to switch colors. So we get the natural log of y is equal to x times the natural log of x. And now we can implicitly differentiate this. So let's take the derivative with respect to x of both sides of this equation. And I'll switch colors again. Nope, that's not what I wanted to do. D dx, and I'm writing this just so you know what I'm doing, is equal to d dx of x natural log of x. So the derivative of this expression with respect to x is equal to the derivative of this expression with respect to y times the derivative of y with respect to x. So what's the derivative of this with respect to y? Well, it's 1 over y. 1 over y times the derivative, just the chain rule, times the derivative of y with respect to x, dy dx is equal to, and remember, just mechanically, if you want to make sure you're doing it right, you just take the derivative with respect to y and you multiply it times dy dx. That's just the chain rule. Equals, and now we take the derivative of this. Well, now we can just use the product rule. The derivative of the first, right? It's this times this. So what's the derivative of x? It's 1. So it's 1 times the natural log of x plus the derivative of the second term, 1 over x, times the first term, times x. Let me clear that up there. I'm already over time, but I've become a YouTube partner, so my videos can be longer. But I don't want to make them too long because you'll get bored. All right. So let's simplify this. We get 1 over y dy dx is equal to the natural log of x plus, well, that just cancels out and becomes 1, right? And so we have the derivative of y with respect to x is equal to y. I'm just multiplying both sides of this equation times y. y times the natural log of x plus 1. Now you might say you're done, but some people just don't like it. The change of y with respect to x, they don't like it being defined in terms of y. So let's substitute. We know that y is equal to x to the x. So that equals x to the x times the natural log of x plus 1. So another way of saying it is that y prime, or the change in y with respect to x, or the slope at any point of this curve, is equal to x to the x, natural log of x, plus x to the x. I just distributed the x to the x. But that's pretty neat. This is kind of a 5-star problem that you might see in your books, and you might see it in a math competition, and people will be really impressed. And they'd be even more impressed if you kind of recognize this pattern and you're able to find the antiderivative of it and recognize that it is x to the x. Anyway, I've talked for too long. I will see you in the next video.